Hello everyone, welcome to another session of Limits and Derivatives, chapter number 13. Today we'll be discussing algebra of limits, then limits of certain functions, that is rational functions, polynomials, trigonometric functions, and their related theorems. Okay, so let's start with algebra of limits. In algebra of limits, what you have a theorem is, according to this theorem we will apply in the problems. Okay, now what the theorem says is, you have two functions f and g and they both have the limit to be existing. That means let f and g be two functions such that both limit x tends to a f of x and limit x tends to a g of x exist. Then what all you can have for limits, that is if you have the sum of two functions and you have to take the limit of that, you can just separate the limit for the two functions, that is sum of the limits is equal to limit of the sum. So this is the limit of the sum, this is the sum of the limits. So limit x tends to a f of x plus g of x is same as separating the limit and giving to the two functions. So you will get limit x tends to a f of x plus limit x tends to a g of x. Next one is, if you have a subtraction, that is you are taking the difference of two functions and their limit will be same as limit of their difference. Okay, difference of the limits of two functions is same as the limits of the difference. So here you have limit x tends to a, that is limit x tends to a f of x minus g of x is equal to limit x tends to a f of x minus limit x tends to a g of x. The third one is limit x tends to a f of x into g of x, that is the product of the two functions. Its limit will be same as the limit of the product. So limit of the products is equal to product of the limits, like this. Okay, so what you have got is limit x tends to a f of x into g of x will be same as separating the limits, that is giving the limit to both the terms or both the functions separately. Limit x tends to a f of x into limit x tends to a g of x. The fourth one is again division, that is if you take the quotient of two functions and limit of that will be same as taking the limit of them separately, that is limit x tends to a f of x by g of x is equal to limit x tends to a f of x divided by limit x tends to a g of x, provided the denominator should not be equal to 0. That is the condition for every division. And in particular you have a case for the third one. If we are taking g of x as a constant, that is lambda, then this becomes limit x tends to a f of x into lambda. That means that lambda is a constant, means you can take it out from the limit, that is it becomes lambda into limit x tends to a f of x. So this is one theorem which whose statements which have been given can be used in your problems. So the next topic which we are considering is limits of polynomials and rational functions. So first of all we should know what is a polynomial. We know that f of x, if I am taking a polynomial in x, I can write f of x as a naught plus a1x plus a2x square plus etc plus an x raised to n. So this is a polynomial of degree n. If I say that an is not equal to 0 and ai's are all real numbers. Okay, so these are all real numbers and n is any natural number, right? N belongs to capital N. Now the thing which we have to find out is limit x tends to a f of x. What will happen to that? Limit of polynomials. So I have taken a polynomial function. So polynomial functions limit will give you what that we are looking at. For that, first thing which we know that we will consider, which is limit x tends to a f of x, limit x tends to a x can be written as, we are just simply replacing this x with a. So you are getting a. This already we know. Right? Now if I am extending this to x square, that is what will be limit x tends to a x square, that can be written as limit x tends to a x into x, that is I have split and written x square as x into x. Now this is of the form two functions product, limit of the product of two functions. So I can write it as, I can just split the limit to both the terms separately, both the functions separately. So I will get limit x tends to a x into limit x tends to a x, and this is a. So you will get here a into a, which is a square. So first what we have started with is limit x tends to a x square and you got it to be a square. That is simply you are just replacing x with a, so that you will get a square, right? Now in general, if we generalize this by induction method, for one you have proved, for second, then in general what will happen to n. So you can say that in general, if you have limit x tends to a, x raised to n will be nothing but a raised to n. So why we have considered all these things is we are just applying this, that is the limit x tends to a for this function, polynomial function, and what at last we will get, we will see. Okay, so we are starting with this function f of x and we are just applying limit x tends to a for this polynomial function. So limit x tends to a, f of x is equal to limit x tends to a of the whole term, that is in the right side, a naught plus a1x plus a2x square plus etc plus an x raised to n. Now according to the algebra of limits, what we have seen earlier, if you have sum in between, you can just separately give the limit to each term. So now I am just going for the first part of that algebra of limits, which is limit x tends to a, I can write a naught plus limit x tends to a1x plus limit x tends to a2x square plus etc plus limit x tends to an x raised to n. Now again, for this is a constant, it doesn't have any x, so we need not replace anything, it will become no change, it will just have that value as such, that is a naught. Now for the second term, again we have seen in a particular case of the third property, that is if you have a constant as a product of a function, you can take out that constant and then limit will be applied to the function only. So if this is lambda, you can take out. So a1 is also a constant here, so that because we have said that ai's are real numbers, they are constant values. So you are just taking out a1 and giving the limit to the x term. Okay, now this becomes like this, a1 into, next one you will have here a2 you can take out and you will give limit to the term x square plus etc plus an can be taken out, limit x tends to a, x raised to n. Now again we have discussed that limit x tends to a, x is a, so this term will become a, right? So we'll have a naught plus a1 a plus a2. What will happen to this? This is a square, so a2 a square plus etc plus an, limit x tends to a, x raised to n is a raised to n, so here you will have a raised to n. And this is actually same as if you see for f of x, wherever you have x, if I replace it with a, I will get a naught plus a1 a, right? Instead of x a, instead of x a, like that you are getting. That means this which you have got in the right hand side is same as f of a. So what you got limit x tends to a, f of x is same as f of a. That means whatever be the function of x you have, limit x tends to f of x is same as replacing x with a in that function. Now considering the rational function, we will just see what is the limit of a rational function. So for that, first we are taking a rational number. Suppose f of x is a rational function, so that it can be written as a quotient of two functions of x. Suppose h of x by g of x, where both h of x and g of x are functions of x, that is that they are polynomials of x or in x, such that this denominator is not equal to 0, right? Now we are just taking limit on both sides. Limit x tends to a, f of x will be equal to limit x tends to a, h of x by g of x, and that is same as, again the fourth property says that if you have limit of a quotient is equal to quotient of the limit. So here what you will get, you can just separately give the limit to both the numerator as well as the denominator. So you will have limit x tends to a, h of x divided by limit x tends to a, g of x. Again in the earlier thing, that is limit of polynomials, what we have studied, limit x tends to a, h of x will be same as h of a. So this will give you h of a and this will give you g of a. Okay, so this is how it works in, that is the limit works in rational functions. Now for this, if the denominator g of a is 0, then you have two cases, that is either h of a is not equal to 0 or h of a is equal to 0. Now suppose h of a is not equal to 0. For that, if you get h of a is not equal to 0, that is the first case is h of a not equal to 0, then you will say that the limit does not exist because the denominator is 0 and the numerator is not equal to 0, so that will give you the limit does not exist. Now for the second case, that is when h of a is equal to 0. Okay, for the second case, h of a equal to 0, what we are doing is we are just taking h of x and g of x as a representation. That is, if you have h of x, if you can write or split this as x minus a the whole raised to k, that is any power of, okay, that can be any power, into the remaining polynomial, that is into h1 of x, and g1 of x is written as x minus a the whole raised to some other power, okay, some other power of x minus a into this is g of x into g1 of x, like this you are writing. Okay, now we will start with what will happen to f of x, or the limit of f of x, limit extends to a f of x. We are just replacing the value for these h of x and g of x. What h of x has been taken as is x minus a the whole raised to k into h1 of x divided by x minus a the whole raised to l into g1 of x. Now here again you have two cases, that is either k can be greater than l, that is the power of this can be greater than the power of that. At that time what will happen, that is I am taking if k is greater than l. So when you have k is greater than l, that means the denominators, this term will be completely gone. And why we are taking like this, if you are taking g of a, no, here already we have seen that taken that g of a is 0. So if I substitute here g of a, you will get a minus a, this is totally 0. Okay, so that is being satisfied with g of x by this condition. Now what the condition is, here what we are doing is, this is lesser, we have taken if k is greater than l, that means this power is lesser, means you can just cancel out this completely. So the remaining thing will be k minus l, whatever has been cut out, after that the remaining thing. So that we can represent this as limit extends to a x minus a the whole raised to k minus l into h1 of x divided by g1 of x, right? Now what is the thing is, we are just giving the limit. So while giving the limit, what will happen is this will become a minus a the whole raised to k minus l into h1 of a divided by g1 of a, right? Now a minus a, this will give you 0, so it is 0 into h1 of a divided by g1 of a. We don't know what will happen to g1 of a and h1 of a because we have taken only g of a 0, not g1 of a. Okay, after cancelling out this thing or separating this, we don't know whether this will give you a 0 or not. That's why we have written it like this, but 0 into something, this will give you 0, that we know. So what happened is you got, that is if g of a is 0 and h of a is also 0, then you can just rewrite them like this, that is you are cancelling out, or you can say you are just simplifying and then again substituting the limit. At that time you are getting it to be 0. Now if the other condition, that is k is less than l, if we take k is less than l, then the limit is not defined, okay, because the denominator will contain the much bigger term, that is the power will be higher in the denominator. That means after cancelling out the common part, you will get the denominator as l minus k. That means x minus a term will be there in the denominator, so that when you replace the limit, you will get 0 in the denominator. That's why here the limit is not defined. Okay, clear? So this much is your for the rational functions. Next is the theorem. For any positive integer n, limit extends to a x raised to n minus a raised to n divided by x minus a is equal to n a raised to n minus 1. And this is again true for if the power, that is n, is instead of positive integer, if you are having a rational number also, then also you can apply the same result. Okay, now moving on to the proof. Actually, when you substitute directly, here you will get 0 by 0 form. If you apply limit here, you will get a raised to n minus a raised to n, which is 0 in the numerator, divided by a minus a, which is again 0. So it is 0 by 0 giving. So directly we cannot solve this problem. So for that we are just using this result. Okay, now how to prove this is, you can write x raised to n minus a raised to n as x minus a into x raised to n minus 1. After multiplication you will get this only, okay, plus x raised to, the power of x will decrease here and here you will get a, then see, you can just multiply these two, you will get this term, okay, and remaining middle term after multiplying, that will get cancelled and you will get only the last term when you expand. Then next, the power of x will again decrease, it will become n minus 3 into a square here. Power of a is increasing and power of x is decreasing, plus etc. plus this will become, when x raised to power of x is 1, this will become as a raised to n minus 2. So that the power is actually in total maintained as n minus 1 only. Here you don't have a's power, here a's power is 1, so that this will give you in total n minus 2 plus 1, which is n minus 1. Like that, here also you will get n minus 1 as the total power, and the last term is a raised to n minus 1. So that when you multiply now, this first term, that is x into this term, and a into a raised to n minus 1 will be left, that is x raised to n minus a raised to n. So we can represent this like this. Now what is the question is this divided by this term. So I am just taking that term to the left hand side, so that I will get it as x raised to n minus a raised to n divided by x minus a is equal to x raised to n minus 1 plus x raised to n minus 2 into a plus x raised to n minus 3 into a square plus etc. plus x into a raised to n minus 2 plus a raised to n minus 1. Now taking limit on both sides, limit x tends to a, x raised to n minus a raised to n divided by x minus a is equal to limit x tends to a of the total, that is x raised to n minus 1 plus x raised to n minus 2 into a plus x raised to n minus 3 into a square plus etc. plus x a raised to n minus 2 plus a raised to n minus 1. Now applying limit to each of the terms separately, again whatever we have studied in algebra of limits we can apply separately, and again for each term if you have a constant that can be taken out and the limit will be applied to the x term or the polynomial. So here you will get first term as limit x tends to a x raised to n minus 1 plus a can be taken out in the second term, and this will become limit x tends to a x raised to n minus 2 plus a square can be taken out, limit x tends to a x raised to n minus 3 plus etc. plus a raised to n minus 2 can be taken out, limit x tends to a x plus, here if you apply the limit then also there is no difference because you don't have any x term in the last one. Now applying, that is replacing x with a, you will get first term as a raised to n minus 1, second term as a into a raised to n minus 2 plus third term a square into a raised to n minus 3 plus etc. plus a raised to n minus 2 into a plus, this will not be disturbed, so it is a raised to n minus 1 itself. Now see, a raised to n minus 1 plus this is a raised to 1, so the total power will become as a raised to n minus 1 plus here again when you add the power you will get a raised to n minus 1 plus etc. plus a raised to again a raised to n minus 1 plus a raised to n minus 1. So how many a raised to n minus 1 are there in the sum? N times, right? 1, 2, 3, 4 etc. n times. So you will get n into a raised to n minus 1. So that is what its proof is. Okay. So limit x tends to a x raised to n minus a raised to n by x minus a is equal to n into a raised to n minus 1. So now we are discussing certain theorems in limits of trigonometric functions which will help us to find the limit of certain trigonometric functions. Okay, so the first theorem is, let f and g be two real valued functions. Real valued functions mean its range, or you can say codomain, will be the real set, and both have the same domain, and the domain can be any subset of real numbers or the real numbers also, such that f of x is less than or equal to g of x. So this is the condition given. You have two functions, real valued functions, such that the condition is f of x for any value which you take from the domain, the function f of x is giving the lesser value or equal to value to that of g of x. Okay, that is given as the condition. Now for sum a, which is again in the domain of the function definition, if both the limit exist for that point, that is limit x tends to a f of x as well as limit x tends to a g of x exist, then the limit of them will also follow the same condition as that of the function. That is, limit x tends to a f of x will be less than or equal to limit x tends to a g of x. That means you have here f of x and this one is g of x. Now in any part you can see that here always f of x function is going in the downward position as compared to g of x. So g of x is having the greater value than f of x for any point in the domain, and at some point the same point means they will get the same value because the function can have equal to also. So f of a is equal to g of a if you can have, or it can be less than. So at that point, if the both the limit exist, then you can say that whatever the function, both the functions are having, the same condition will be followed at that point for the limit also. Okay, and it is giving actually giving way or paving way to another theorem, which is sandwich theorem. It is also having, sandwich means what? You have two bread pieces and in between you have certain fillings, right? So in that manner you will have the other one. So next one is sandwich theorem. Here you have three functions, f, g and h. They are real functions, and the condition is f of x is less than or equal to g of x less than or equal to h of x. Okay, then that is, this is true for all x in the common domain, that is for all of them you have the same domain. In the common domain, whatever values you are taking, for that this will be satisfied, that is f of x less than or equal to g of x less than or equal to h of x. Okay, now for some real number a, if you have limit x tends to a f of x as L, and that is the same value for limit x tends to a h of x, that means for this one and for this one, if you have the same limit value, then in between function, that is g of x, will also have the same limit value. That is the theorems. Okay, that is sandwich theorem is saying that if limit x tends to a f of x is equal to L equal to limit x tends to a h of x, then limit x tends to a g of x will also be L. So you have three functions in such a manner that for all values you have f of x is less than or equal to g of x less than or equal to h of x, and at a particular point a, if we take limit of this function and limit of this function is same, then the limit of the in between function, that is g of x, will also have the same value. Very important theorem, which is you have two important limits here, that is limit x tends to 0 sin x by x is equal to 1, and limit x tends to 0 1 minus cos x by x is equal to 0. So here if you replace directly, you will get sin 0 by 0. Sin 0 is 0, so 0 by 0 form. So whatever you have that 0 by 0 form, that its limit has been found out already, which is taken as 1. Here again if you replace 0, you will get 1 minus cos 0. Cos 0 is 1, so 1 minus 1 is 0, and the denominator will also become 0. So it is again in the 0 by 0 form. But limit x tends to 0, 1 minus cos x by x is taken as the value as 0. Okay, so these are the two important theorems or two important values of the limit which you will use in your problem solving process. One more thing which you should know is limit x tends to 0 tan x by x is 1. Okay, so these three things are very important, that is limit x tends to 0 sin x by x equal to 1, limit x tends to 0 1 minus cos x by x is 0, and limit x tends to 0 tan x by x is also equal to 1 as your sign case. Now two more important limits are limits of exponential and logarithmic functions. First one is limit x tends to 0 e raised to x minus 1, e raised to x is, this is not in the power, okay, e raised to x minus 1 whole divided by x is equal to 1, and limit x tends to 0 log of 1 plus x whole divided by x is equal to 1. These are also very important in solving problems.